Okay, so I have to say, mostly I will speak about joint work with Christian Urech and Andriy Regeta. Okay, maybe I start just to say what the plan is. So, and for that, I just say K is a field which will be algebraically closed. Sometimes it will have more properties, and X, this is just an irreducible variety over K all the time. And of course, Bir X is just a group of birational transformations. Okay, my plan is that I will speak there are two parts. One is about the structure of algebraic families of birational transformations. And another part is then really about Borel subgroups. Which I will abbreviate with BS in BRX. Okay. And so that it's even a bit more structured, I say here I will speak first about basic notions. Second, structure of BRX and some consequences of it. Then birational transformations, preserving a vibration. And the last one here is about Rosenlicht quotients. Then here I will speak about basic basic examples. Known results. That's the first. Second is unipotent elements. And some tools. Third, this is like the main thing, boundedness of length of Borel subgroups. And fourth will be about Borel subgroups of length 2n minus 1. So I have to say the n is always the dimension of X. And the last one will be about examples, or the example of a Borel subgroup of length 2n minus 2. Is it readable? Maybe I should write bigger. Okay, I will do. Oop. Okay, so let me start with the basic notions. So the principal idea is that BRX is a group, but it's somehow nice, and you already did this, I think, to study birational transformations in families. Okay? So let me recall what I mean with this. So we are here with the basic notions. So algebraic family of birational transformations. With this, I mean I take some parameter variety X, some birational map to it, okay? So I have here some open subsets where it is defined, and I want that it surjects onto A, where this birational map is defined, and the diagram should commute, so it is an A birational map, okay? So associated to it, I can look at some map, rho theta, which goes from A into Bx, which just sends A to x is mapped to theta of Ax. Okay? And these kind of maps I will call morphisms. And rho theta, the image, is an algebraic subset. Okay, good, good. Yes, then using these morphisms, I take, probably this is stuff that is already, I don't know, is this done already in the first week, or then it's just a recalling? Or, okay. Okay, so it's good to recall. Good. Okay. So this is the notion of an algebraic family of birational transformations, and these morphisms, they induce a topology on Brx. And so I take the finest topology on Brx such that all morphisms are continuous. Yeah? Maybe it was called Zariski topology, or yeah. Good. And there is a notion of dimension. So if I have any subset in Brx, then its dimension is defined as the supremum over all dimension of A, where it runs over all injective morphisms to Brx. So injective morphism, such that rho of A is contained in S. Okay, so this is some kind of notion of dimension. In fact, it was introduced by Ramanujam in a slightly bit different context, where he studied somehow the analogous stuff for automorphism groups. Okay, good, good. Yeah. Algebraic subsets are usually, yes. Yes, but they will be constructible. But yes, I could also call them constructible, yes. Yeah. Yes, but I mean, also I will say later, it turned out that if I have any morphism, it will map constructible subsets. I mean, constructibility makes sense if one has a topological space. So with this, when I take here a constructible subset, it will be constructible inside here. Yes. Which is the image of... Yes. Yes. Yeah. Okay, good. So, yes. So there is some kind... I mean, there is a slight thing. If I have here something constructible, and I take the image and it is constructible, then this is in principle not a morphism, because when I take here something constructible, it has not the structure of a variety. So, okay, good. So, yes, so good. These are somehow the basic notions, and I would like now to say something about the structure of Brx. So if one studies affine algebraic varieties, then the automorphism group of an affine variety has a so-called int group, which is some kind of a nice structure that one which somehow says it's like a bit a replacement of compact open topology, so that one has still a topology on that transformation groups. Okay, now Brx cannot have the structure of an int group. I will not comment more about that, but it has still something which is quite near to it. And the statement is as follows. I write it down and then I will comment more. So there exist closed morphisms pi d from ht to Brx for all d greater or equal than 1, such that the following holds. First of all, pi 1 of h1 is inside pi 2 of h2, inside and so on. Then the union of all them is everything. So this is pi d of hd. Here x has the inductive limit topology with respect to all these sets here. Okay, so it resembles, in some sense, a bit int groups for those who know a bit about them. And it satisfies the following universal property. For all morphisms rho from A to Brx, there exists a covering AI of A such that rho restricted to AI factors through some pi di. Okay. So if I have any morphism, I can cover my A such that each piece factors through one of these maps here. Okay. And the last thing about this general structure I want to say is the fibers of pi d are projective bases. Okay, it's important to say that all this stuff was established in case when X is the projective space by Jean-Philippe Furter and Jérémy Blanc. And what we did is just we analyzed the proof and we just say, okay, it works also for all varieties. So let me give just, I don't really prove that. Is the statement clear? Please ask questions. Yes? Okay, it's a good question. What means, what is now the structure? Ah, sorry, HD is a variety. Sorry, yeah. Yeah, so this is really a variety, yes, yeah. That was the question, or? Yeah, okay, good. Yes. This HD is quasi-projective, yes, yeah. And in fact, this follows from the construction. So the construction goes as follows. We embed X into, let's say, P. Okay, Pn is now a bit bad, so I should change here slightly my notation. Yeah, so I take Pm, okay, as a closed non-degenerate subset. And then I look at kx0 to xm modulo, and in fact in the degree d, so homogeneous polynomials of degree, modulo the elements of degree d in the vanishing ideal, and this one to the power m plus 1, and of that I take the projective space. Okay, so this is a finite vector space, and I take projective space of it, and inside here I look at WD. So these are the f's, or f0 to fm, such that, now I have to insert here something, such that r of f0 to fm is equal to 0 in k of x0 to xm mod out by I of x. Okay, for all r in the vanishing ideal that are homogeneous. Okay, so this one here is a closed subset. Okay, and when I have any f in WD, I can associate to it some psi f, which is now a rational map from x to x. Okay, so this WD just says I take the tuples, okay, that map rationally x into x. Okay, so therefore I get here a rational map, and then HD. This is just defined as those f in WD, such that this psi f is birational. And this one here, one can show, and this is the important thing, that this one here is locally closed. So therefore the HD is quasi-projective. So that's the construction, and then with this construction one has to prove all these properties. Okay, some consequences, some easy consequences first. Let's say about the neutral component. So I take a G inside Br(x), which is a closed group, closed subgroup. Then I can look at the connected component in G, and this has a countable index. And yes, maybe the reason for that is just I can take pi d inverse of G. Yes. So this is inside HD, something closed. Okay. So it has finitely many connected components, and now so this implies that also pi d of HD intersected with G has finitely many connected components. Okay. But now the G is just the union of all the, yeah, maybe I don't have to write this down. So the G is now the union of all these. So it's a countable union of finitely many connected components, so it has finitely many connected, countably many connected components. Okay, so that's something very basic. Something other quite basic thing, connected components. So we assume now that G is in addition not only a closed subgroup but also connected. Okay, And in this case, then we have the following. For all G in G, there exists an irreducible closed, I stay with algebraic subset, okay? Algebraic subset Z in G such that the identity and G are both in Z, okay? And moreover, I can write my G as the union of GDs, where every of these GD is an irreducible closed algebraic subset. Okay? And also here I would like to give an argument for that, as it is quite simple, so So the point is, let's look inside G, and I take here some irreducible closed algebraic subset Z0, and let's say I take another one, and they intersect this in some H, okay? Then I can look at Z0 composed with H inverse composed with Z1, and I can take the closure of it. So this is something which is still contained inside G. Okay? But the point is now that this thing here is still an irreducible closed algebraic subset. Okay? And because H is a common point of Z0 and Z1, it contains Z0 and it contains Z1, so it contains both, okay? So I can always find two irreducible closed subsets that intersect in one point. I can put them in some common irreducible closed algebraic subset. And this is somehow the point how you prove this this statement here, more or less. Okay? I hope. Good. So as I already mentioned, some further conclusions which are a bit more difficult to prove, so I cannot give the proof, are what I said already. There is a Chevalley type theorem. Saying that morphisms preserve constructibility and another one which is quite useful when one works is some fiber dimension formula. Fiber dimension formula. Saying that if I have any morphism from A to Br(x), so this is a morphism, then there exists some U in A which is open and dense, such that when I intersect U with rho inverse of rho of U, and I take the local dimension at U of this set, this is exactly the same as the dimension of A minus the dimension of the image of A and the closure of it for all U and U. That kind of thing one usually uses in algebraic geometry holds also here for morphisms. So it is just like many properties that work in algebraic geometry and one uses all the time work here as well, and we give an argument for that. And the last tool that I want to mention is about algebraic subgroups. So I take now G in here X, closed finite dimensional subgroup with finitely many connected components. Okay, so this is satisfied when G is an irreducible algebraic subset that is a group. Okay, also having this gives a unique structure, although there exists a unique structure of algebraic group G, sorry, I should say on G, such that the following universal property holds. So I take here the map from G to here X, with the image is just G, okay? And this is now has the structure of an algebraic group. So if I have any morphism, which is also a homomorphism from any other algebraic group inside here, such that, let's say this is rho, such that rho of H is contained here in the image of that one, it factors through this one uniquely. Okay, so this is maybe also in some version you heard of this in the first week, maybe. I don't, not really. Okay, good. So yes. Good. So the idea behind here, and this is a bit with all of these, is the fact that if I have, as this is just a very rough idea, cannot give all the proofs. So, but if I take any set in Bir X, which is irreducible and closed algebraic subset, okay, then there exists a row from W to Z, a morphism, which is also surjective, and it is closed. Such that the following holds. There exists a W prime in W, which is open, dense, and saturated. And one has the following decomposition. So when I restrict rho to W prime, from W prime, I have a map to some U, and then to rho of W prime, which is something inside Z. This one is a homeomorphism, and this one here is finite and flat and surjective. So this is some kind of a, what is the statement of this is, when I start with any irreducible closed algebraic subset, I can find some closed parametrization of it, such that generically it is really nice, okay? And this is somehow, this is a major tool that we used for proving these three things. Okay. Are there so far questions? Is it clear? Perfect. Good. So some example that I would like to show you which will be very useful in the future. So I take now, I'm now in the situation that G in Br(x) is an algebraic subgroup. And I assume that H in Br(x) normalizes G. Okay. Now I consider the embedding of G into Br(x). Okay. So it's an algebraic group, so I have this embedding. And I look at J, which goes from G to Br(x). And I map my G to H composed with iota of G composed with H inverse. Okay, so this is of course again a morphism. And it's a homomorphism, and its image is by definition inside G. Okay, so I can apply the universal property here. So I have G to Br(x), which is my iota, and this is my J. And so I have here a unique, in fact here, isomorphism, such that the diagram commute. Let's call this FH. Okay. So what is the upshot of it? And this is something we will use later, that if H in Br(x) is a subgroup that normalizes G, then the map which goes from H into the group of algebraic group automorphisms of G, this is really a homomorphism. So which is just H is mapped to G is mapped to H composed with G composed with H inverse. Okay? So with what I said here is just like this stuff here, this conjugation is really an automorphism of this algebraic group G. Okay? Good. So I will come to the third thing. This is about birational transformations which preserve a fibration. Okay, so very useful was for our study to have some kind of study birational transformations that preserve a fibration and look what happens there with continuity and so on. So let's say pi from x to y is a dominant morphism. Okay, and big K is just some algebraic closure of the function field. And so we can look at the geometric generic fiber. Okay, spec K. Good. And we assume that xk is integral, which is the same thing as saying that k of y in k of x is algebraically closed, and this extension is separable. Okay, and then we can look at the subgroups of Br(x), namely those phi such that they induce a birational transformation down on y. So there exists a phi bar in here y such that phi pi is the same as phi bar composed with pi. And I can look at Br xy, which are just those phi such that pi composed with phi is the same as pi. So those that give the identity down on y. Okay, good. And we proved that, in fact, the natural map from beer x to pi to beer y, and also beer xy to beer k xk. Here, this is just G is mapped to its induced map in beer y, and phi is just a pullback on the geometric generic fiber. Both are continuous. Okay? And here we showed slightly more that if I have any morphism going into here from a normal variety, and I compose it with that, gives me again a morphism. Okay? And that was somehow the major point to do that. Good. And another tool that I would like to present, which is, I would say, super useful in this study, are Rosenlicht quotients. Rosenlicht's quotients probably also appeared already a bit briefly, okay, and in the classical setting. Okay, so the idea is that there exists also some type of Rosenlicht theorem in this more general setting, where I take a G in beer X, which is a closed connected subgroup. Okay. And before speaking about Rosenlicht quotients, I should say what I mean with an orbit. So I take some x in X, and then the orbit on the G are just the G of X, such that X is in log iso of G. And this is just the open subset where G is locally an isomorphism. Okay? So this is an open subset of X. And this I define as the orbit on the G. Okay? And then the statement is, so we proved that there exists a Rosenlicht quotient for the action of G on X. So what I mean with this is there exists some x0 in X, which is open, dense, and G stable, meaning it's a union of G orbits, okay, such that the following hold. Pi from x0, and some morphism pi from x0 to y, such that the following holds. So pi is open and surjective, and the fibers are G orbits. And the second is something about the functions. For all u in y open, we have a map from the regular functions on u, okay? Namely, I can pull back them on regular functions on x, on pi inverse of u, which are G invariant, and this one has to be an isomorphism, okay? Yes? Right. Yeah. Yes. I have a partial, yes. But you can think of, you can really think of, I can see this rational, I can see this as a rational map, and G acts on the function field, and so there it's constant. Yeah. Yes. And moreover, and this is the full thing, ky is just the invariant field of x, and this one is in kx algebraically closed, and the extension is separable. Okay? Meaning we are here with the Rosenlicht quotient exactly in this situation where the geometric generic fiber is then integral. And this is useful for doing inductive steps. Okay, some quick consequence is that saying that all invariants are constant is the same thing as G acts with an open ends orbit. Okay. And another corollary which is super useful, I would like to mention maybe here. Let me clean a bit. Maybe I should mention that there was a generalization for this Rosenlicht quotient theorem in the context of automorphisms of X by Popov. But I mean, we couldn't use it because we really needed it in this generality. Up. So. Yeah. Yes, yes. This is not an obstacle. No. I mean, I don't say that G acts regularly on x0. That I don't say. This is wrong. This we cannot find. So a second consequence, which will be very useful for later on, is if we, in addition, assume that G is commutative and it acts without invariance, okay, then we have the following points. So G is then in Birx, an algebraic subgroup, and the centralizer of G is the same as G, and we have that the dimension of G is exactly the dimension of X, which is n. Okay. Maybe okay for the Rosenlicht. I mean, let me think about the time. No, it's too much. I mean, what I can say is just like it follows more or less the strategy of the classical Rosenlicht the theorem. So roughly the idea is just, what is this y? It's just the point that I can take the invariance, where I have written it down here, kx of g, and this is a finitely generated field extension of k. And so I take these, and then I take some y, which has exactly these functions, and then the quotient is given. And this is somehow how one starts the construction. But it is more difficult because we don't, I mean, G is not an algebraic group, yeah? So it becomes more difficult, but yeah. But maybe let me give some idea for this corollary too. So I take here some set in G, which is irreducible and closed algebraic subset. Okay, such that the following holds. I mean, okay, this thing tells me that I find some dense orbit. Okay, and I can manage to find such a set such that this one here still contains some u, and this one here is open inside, okay, for some point. Maybe let's call this point x0. Good. So having this, I can take now some phi in the centralizer of set, okay? And so because U is an open dense subset, I can find U0 and U1 in U such that phi of U0 is equal to U1. Okay? Because phi of U intersects U. So therefore I can find this. Good. So but this U is in set x0, so I can write U as f of x0, and U1 I can write as h of x0, where fh are elements of set. Okay? And then I have, for general set in set, I have the following. So, let me plug in this into here. So I have phi of f of x0 is h of x0. Now I can compose with any element of set. Okay? And when I take a general one, because phi commutes with set and set is something commutative, so I can take it inside. So this means phi of f of set x0 is the same here as h of set x0. So this works for general set in set, and so f phi composed with f is the same as h. Okay? What we learned of this is that, okay, we started with any element in the centralizer of set, and we showed that I can compose it with an element of set, and then I get an element of set. So the centralizer of set is contained in set composed with set inverse. Okay? But this one, of course, has the centralizer of G, and G is inside here. But set composed with set inverse is in G. So I have all equalities. And so this says in particular that G is an algebraic subset, so it's an algebraic group. And we have it. It's something closed in general, but it's not. It doesn't have to be an algebraic subset. But here, this one here is an algebraic subset, and then I compose it with that algebraic subset, and so this one is algebraic. Yeah. No. In general, it's not. This is not true. Good. Yes. Okay. So that was the stuff that I wanted to say about the first part of my exposition. The point is a bit that tomorrow I have 1 hour, so it will be not divided one by one, so it's a bit different. Are there questions? No. Okay, good. So let's continue with Borel subgroups in BRX. Luckily, in the talk of Mark, we learned what a solvable group is. So I just have to say what a Borel subgroup is. So for that, I can say maybe G is not so, I don't know. Yeah, maybe. Let's say G is some group, which is also a topological space. And then B in G is a Borel subgroup if B is solvable, connected, and maximal with these properties. This will then be a consequence. When it is solvable, then I can take the closure and then for connected also, yeah. But it's true, it's a consequence. They are then closed, yes. So prominent examples are, of course, the upper triangular matrices in, let's say, GLM. Okay, so this is a Borel subgroup. And in fact, any Borel subgroup is conjugate to it, also to these upper triangular matrices. And this holds for all. So this is true for all connected algebraic groups. What I mean with this, there exists a Borel subgroup, and all Borel subgroups are conjugate to that one in any connected algebraic group. Okay, so these Borel subgroups, they are quite useful in studying algebraic groups, and one has some kind of analogy between algebraic groups and transformation groups, and one would like somehow, I mean, it's quite natural to also study the tools from algebraic groups in birational transformation groups in order to understand them slightly a bit better. Okay? Because it will be a consequence. Okay. Sorry. Maybe in this generality, no, because this is true. This is true. And I don't say this because BRX is not a topological group. That's the reason, yeah. But okay, it's true. Here, it's not a consequence. But in the examples that we, also for example, here it is a consequence, and in BRX it's also a consequence, the closeness. Yeah, yeah. Okay, yes, yes, right, yes, yes. That's true. Good. So if one would like to study Borel subgroups in BRX, then as here with this example, it's somehow tempting to try to generalize this example. Okay? And yes, one can do this. So further example, Bn, these are the A1 x1 plus B1 and 2an xn plus Bn, where ai, bi are rational functions in x1 to xi minus 1, and ai should not be 0. Okay, so this is something inside the Cremona group. Okay, this is some subgroup, and it has exactly this triangular form. So A1 and B1 are constants, and then A2 B2, they depend on X1, and so on. Okay? And in fact, this one here is a Borel subgroup. This is by Popov. And the length of this Borel subgroup is 2n. This is due to Furter and Heden. No. Yes. Okay, and with the length, I mean the derived length. Sorry, I changed there slightly the notation. Good so far. So what one can ask now, having this En, first of all, are all, I mean, as we have here, all Borel subgroups are conjugate to that, and so one can ask this also in this context. It's quite natural. And in fact, it is also conjectured by Popov that, but no, one can ask this, but the conjecture of Popov is, no, this is not the case, at least when n is greater or equal than 5. So conjecture is here An has exotic Borel subgroups if n is greater or equal than 5. And with exotic, I mean one which is not conjugate to En. Okay. Yes. In order to prove the conjecture, or what? How? The point is, okay. Good. So, I mean, yes. So, a bit later, Jean-Philippe Furter, and this is in that paper, and Isaac Heden, in fact, completely classified all Borel subgroups in dimension 2. So the Borel subgroups in sphere A2 are up to conjugation the following. So pi f of A1, which is defined as x1 and then ax2 plus bf over bx2 plus a, where ab are rational functions in x1 and ab are not both 0. Okay, and the f in kx1 is square free. And x2 square minus f, this is some curve in A2, let's say, or in P2, and I can resolve it or whatsoever. What I want is that this curve here, sorry, I should here equality, this curve is not rational. And the second one is, okay, I have a GM, a semi-direct product with, sorry, it's in this way, pi x1 of A1, okay, where the GM is given by t square x1, t x2, and t is some element of k star. And the last one, of course, is the B2. Okay, and these are all. So this one? This one here? Yeah. Because then this one here is a rational curve. So this is just this case here. It's not of this form here. Yeah. Yeah. Yes. 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 Yeah. Okay. But what we see here is at least what is quite nice is that, sorry, I should say something about the length. This one here is abelian, so the length is equal to 1. Here the length is equal to 2. And of this we know the length is equal to 4. Okay? So at least we see that Borel subgroups of length 4 are all conjugate. So one may ask, what happens? What happens in higher dimensions? Okay. And in order to tackle this, I have to introduce some tools. And this will be the second here about unipotent elements and some tools. So, something I forgot to say, which is quite important. So in the first part, K was just any algebraically closed field, but in the second part, maybe I write this down here, I really want that I have a characteristic 0, and I want that K is uncountable. So in principle, just the complex numbers. Okay, so for the whole part. And this is now important for this unipotent element. They proved it over the complex numbers. But I would say so, yes. But to be convinced, I have to study more. Good. So I will call a sigma in Bir X unipotent if sigma is part of a GA action. And maybe to say, okay, I already here denote this GM. So GM is in principle just a shorthand for K star, and this GA is just K with addition. Okay. And the proposition is is part of a is part of a, I should say like this, of a rational GA action. Okay. And the proposition is as follows. So this is some kind of descent result. So I take a morphism from X to Y, which is dominant, and the geometric generic fiber should be integral. Then for sigma, sorry, and I take some sigma in here X over Y, so some birational map that induces the identity on Y. Then the following holds. Sigma is unipotent if and only if the pulled back sigma k in here x k is unipotent. Okay, so this is a yes. So this is something quite important for us. So I would like to give a sketch of this. Let's say if I start with something unipotent, then of course when I pull it back, I get something unipotent. So the harder direction is in the other direction. So yes, by definition, I can say there exists a morphism which is also a homomorphism rho from GAK to BRXK, okay, such that sigma k is in the image. This is what I mean with it is part of a rational GA action. Okay? This is just by definition. Good. So now the good thing with GA is one can choose coordinates in GAK such that rho of 1 is exactly my sigma k. Okay. Oh, now I need some more space. Oh, maybe I should. Here. Yeah, erase stuff here. Okay, so I can look here at the group generated by sigma k, and as we are in characteristic 0, this one in GAK is dense and fixed under the Galois action. Okay. So this implies that this, maybe I should write rho of this one. So rho of AK is fixed under this Galois group. Okay. So this one here, rho sigma k, this is fixed by the Galois group because it is something coming from downstairs. So this one here is dense, and the Galois group acts by homeomorphisms on BRX. So this one here, sorry, fixed is maybe bad, is invariant, I should say. Okay, so saying that this one here is invariant under the Galois action gives us that then this GAK action is the pullback of GAKY action on the generic fiber XKY. Yeah. Sorry. Yeah, sorry. This is, yes, you're complete, sorry. It is, sorry. Big K and then KY. Sorry. Yeah, thank you. Okay, good. Yes, this is what I meant, but I didn't wrote it. No. Okay, so this is GAKY action on the generic fiber. So this means writing this down. This is GAKY product over KY with this generic fiber to KY. So it's, sorry. And in fact, 1x, by definition, by the choice of our coordinates, 1x is mapped to sigma of x, sigma ky of x. Okay. But now this one here is the same as GA times, let's say, ky. Okay. So this cancels, and this gives me a GA, really a GA action on, as a rational GA action on x. Good. What I would like to stress here is the corresponding statement for GM is wrong. Okay, so it's important to have here GA so that we can make this descent argument. Okay? And let me give an example of this. Yes, I take I take just the usual projection from A2 to A1, and I map XY to just Y. Okay. And I look at my sigma. This is from A2 to A2, and it maps XY to Y times X, comma Y. Okay, good. So this one here is invariant for, also this is a, the sigma is in beer A2, A1. And yes. And when I pull it back now, so my K, this is just algebraic closure of KY. Okay. And when I can pull it back. Yes. So maybe first, let's say this is the X. So the geometric generic fiber in this case is A1K. Okay. And the sigma K is then just given by yeah, let's say x is mapped to yx, okay? Because y is now an element of the constants. Good. So this one here is part of the GMK action, which is just t comma x is mapped to t times x, okay? When I vary here now for all t's in GMK, okay? But on the other hand, the degree of sigma to the power n is unbounded. So sigma cannot be in an algebraic group, algebraic subgroup. Okay, so here this is not possible. So our friends are the unipotent elements. Good. And there is some statement. It's more like a small lemma, which I also would like then to use for the study, which is as follows. So G, this is in here X, something connected and closed subgroup. And H, this is a subgroup of G, which is really a proper subgroup. Okay. And then the first statement is when H is in G closed, then the index of H in G is uncountable. So here we use the uncountability of the ground field. And B is if H in G has a countable index, then and G is solvable, then the length of H is the same as the length of G. And the last one is when H in G is closed and normal, then the length of G mod H circ is the same as the length of G mod H. All these tools I would like then to use in the future. So let me briefly give the argument, as it is somehow easy. So for A, what we do is we take some morphism, rho from V into beer X. This is a morphism. Morphism with rho of V is inside G, and it contains the identity. And I want that rho of V is not contained in H. Okay. So what I do is now I can write my V as now I assume that this this index is countable. So if this index is countable, then I can write my V as the countable union of rho inverse of H cosets. So I take here all H cosets, rho inverse of it, and because there are just countably many of them, so I can write this as a countable union, but this is impossible over an uncountable field, okay? So this is a countable union of closed subsets, so we get a contradiction because K is uncountable. Okay, and for the second statement, because now G, H has in G countable index, when I take the closure of H, it has to be the same as G. Okay? And so we have the stuff with the length. And for the last one, when I have a closed normal subgroup, then yes. So let's assume I have dk of, here I should also say, with the assumption that G mod H circ is solvable, otherwise it doesn't really make sense. Yeah. So dk of G mod H circ, assume that this is that this is trivial. Okay, so this means that the G, I want to assume that this one here is trivial, and then I want to conclude that then for the other one it's also trivial. So this means that the kth derived subgroup of G is contained in H, but this one is connected, so it is in fact inside H circ. Okay, and so we have it that dk of G mod H circ is trivial as well, and then we get this conclusion as well. Okay. Are there some questions, remarks? Okay, good. Yeah. About K. Here. Yeah. You're right. You're right, but yes, but this is no, this is okay because the identity is in row of V, and so I say it is not inside that coset. Then. Yeah. Good. So let me erase some stuff. Yeah, I erase here. So I will come to my third chapter of the second part, which is about boundedness of length, and yeah, in fact it is also about Borel subgroups of length 2n. Okay, good. So as we have seen, still somewhere is maybe this conjecture of Popov that bir an has exotic Borel subgroups. And if you would like to go for that for higher dimensions, it's quite, I think, natural thing to do is to consider these exotic guys that we have in dimension 2. Okay? So let me look at this example here, but we can look at it now not over A1, but just over an minus 1. So it is exactly the same guy here, but just with many more variables. Yeah. So something that I wanted to say here is that in fact this curve here, this is exactly the fixed point locus of every element here. Okay? So this means the fixed point locus of every element here is a non-rational curve. Okay? And one can achieve this as well here when one chooses f a bit general enough. So every So use F general, then every element of this guy here fixes only non-ruled hypersurface. So ruled means it is just birational to P1 times some variety. So when n is equal to 2, this means exactly that this curve here is not rational. Okay? On the other hand, inside Bn, okay, there every element fixes only ruled hypersurfaces. Okay? And if I have any birational map from AN to AN, birational, it contracts only ruled hypersurfaces. So this means if I can find a Borel, if I can find a Borel subgroup which contains this one here, it cannot be conjugate to Bn. Okay? So yes, but what is the problem with that? I mean, as probably Serge thought that one would like to just apply Zorn's lemma and make bigger and bigger. But the problem is that in principle there, the derived length could be bigger and bigger and bigger, and then the union is not solvable anymore. Okay? So one needs to bound the length. Okay? And this is in fact possible, and this is some kind of the main theorem. So yes. So let's say G, this is in pure X, connected and solvable. Okay. Then the following holds. First of all, I can say the length of G I can bound by twice the dimension of X. And the second thing is if this length of G is equal to 2n, then there exists a birational map from X to AN, such that if I conjugate I inverse and then G and then phi, wait, no, I think it is then the other way around, yes? No, it was correct. This is really something which is contained in the standard Borel subgroup. How much time I have? 1 minute. 2 minutes. Okay. Yes. So then I will just say as an immediate corollary of that theorem, and then I will stop. So since now the length is bounded by twice the dimension, I can say every connected solvable subgroup is in a Borel subgroup, and all Borel subgroups of length 2n in the Cremona group are conjugated. Okay? This is an immediate corollary of that theorem. And tomorrow I would like to give a sketch of that result and say further results. Then I would stop here. Also characteristic 0 I used for this unipotent business. Also directly the argument is now gone, but when I take the subgroup generated by one element, it's not dense. And then, yeah. And the uncountability I used so far here in this lemma. And this will be used then tomorrow, so far, yeah. I don't say it's, maybe it could be circumvented, but yeah. Oh. Yeah. Yes, but they are. Yeah, they are. Yeah. So this is, I mean, there is another approach with, I don't know whether it was discussed with the Hilbert scheme. Okay, so when one takes a birational map, I can look at its graph in the product, and then I can study it via the Hilbert scheme. But this approach was done by Hanamura. But the problem there is this is not at all compatible with the group structure. So that's a bit problematic. And there he studied flat families. But we used that, that approach also, but just for studying the generic behavior of algebraic families. So it was important also to look at this viewpoint. But it's somehow, for us, it's not so good adapted because it's not compatible with the group structure. Yeah. Thank you.